You know, from your phone's GPS to the weather forecast you checked this morning, our daily lives are powered by thousands of silent partners circling way, way above our heads. They're pretty much the unsung heroes of our modern world. But that brings up a really good question, right? With Earth's gravity pulling on them constantly, how do all of these satellites actually stay up there? What's stopping them from just falling out of the sky? Okay, let's get into it. Well, the secret isn't about defying gravity. It's actually the opposite. It's about mastering it through something you could call the art of falling. It's this beautiful, delicate dance between two incredibly powerful forces, gravity and speed. At its heart, an orbit is all about that perfect balance. It's not really about floating around. It's about moving forward so ridiculously fast that you perfectly counteract the constant pull that's trying to drag you down. Okay, think about it like this. Imagine throwing a ball. It travels forward, but gravity pulls it down in that classic arc, right? Now, imagine you could throw it so incredibly fast that as it arcs downwards, the Earth's surface curves away underneath it at the very same rate. That's it. The satellite is perpetually falling, but it's moving so fast horizontally that it continuously misses the ground. It's literally falling around the Earth. So, the most important thing to remember is this. An orbit isn't zero gravity. Not even close. It's a state of constant freefall, just one that's perfectly balanced by a massive amount of forward momentum. And, depending on what a satellite needs to do, this balance is struck at totally different altitudes. Not all orbits are created equal. Yeah, you can almost think of them as highways in the sky. And for a satellite to do its job right, it needs to be in a very specific lane. These orbital highways are all defined by their altitude, and that directly impacts how they act and what we can use them for. And this table here really breaks down the two main types. You've got low Earth orbit, or LEO. Satellites there are pretty close, and they are just whipping around the Earth in as little as 90 minutes. But then you have geostationary orbit, or GEO, which is much, much farther out. So far out, in fact, that its orbital period is a perfect 24 hours. It exactly matches Earth's rotation. And as you can see, each one is designed for a completely different job. Let's dig into why. LEO is all about being fast and close. Since the satellites are nearer to us, signals have way less distance to travel. That cuts down on lag, or what engineers call latency. This is absolutely essential for real-time things like global internet from companies like Starlink. And of course, being closer just gives you a much better, sharper view for high-resolution photos of our planet. GEO, on the other hand, is the master of just staying put. Because it orbits at the same speed the Earth spins, it looks like it's just hovering over a single spot on the ground. This constant presence is why your satellite TV dish doesn't need to move around. It's incredible. A single GEO satellite can provide nonstop coverage for broadcasting or weather monitoring across an entire continent. So we know what an orbit is and where they are, but how do we get a satellite into one of these incredibly precise highways? And then, keep it there. This is a story of a satellite's life, from launch all the way to retirement. Getting into that final orbit isn't just a straight shot up. Engineers use the super efficient maneuver called the Hohmann transfer. First, a big engine burn pushes the satellite into this oval-shaped or elliptical orbit. Then it just coasts, swinging way up to the highest point of that oval. The moment it gets there, a second precise burn kicks in, pushing it forward and turning that oval path into the final, stable, circular orbit. It's a really beautiful and fuel-saving move. But once it's in orbit, the work is not over. Tiny little disturbances can slowly nudge a satellite off course. To stay in its lane, it has to do something called station keeping. Now, while it can use small thrusters, many modern satellites use this absolutely ingenious device, reaction wheels. They're basically internal flywheels. By spinning a wheel faster or slower, the satellite itself rotates in the opposite direction. It's an amazing way to make super precise adjustments without using up any precious fuel. But of course, nothing lasts forever. When a satellite's mission ends, it needs to be disposed of responsibly. For those LEO satellites, being close to the atmosphere is actually a big plus. They can be commanded to use that little bit of atmospheric drag to slow down, fall from orbit, and just burn up completely. But for those high-flying GEO satellites, that's not really an option. Instead, they use the last of their fuel to push themselves even higher into a stable graveyard orbit where they won't become a collision risk for anyone else. So from falling with style to navigating these invisible highways in the sky, a satellite's life is this constant, amazing performance. It all comes back to that one core idea. a perfect, high-speed balance that turns the relentless pull of gravity into a graceful cosmic dance.
And that really leaves us with a final thought. With these new mega constellations launching thousands of new satellites, those orbital highways are getting seriously crowded. The huge challenge for the next generation will be figuring out how we manage all this traffic to make sure this beautiful and vital cosmic dance can continue on safely for decades to come.